Out there in the critical obscurity of space, the James Webb Space Telescope has been researching the dark for replies about the universe. It's NASA's new eye above and has been discovering stunning pictures of stars, huge systems, and planets. At any rate, before long, something surprising has been tracked down. Something so enormous it could shake the very spines of all that we know. It has researchers scratching their heads and analyzing whether it could prompt the farthest restriction of everything. Join us as we investigate how the latest revelation of the James Webb Space Telescope could destroy the universe. When we investigate the edge of the universe, it is the noticeable early phase. The observable universe looks like a window through which we can explore the tremendousness beyond the discernible universe. The observable universe envelopes everything that we can currently recognize, measure, and explore using our telescopes and space probes. It's an assortment of stars, galaxies, and celestial bodies within our degree of understanding. At any rate, the discernible universe is just a little piece of the whole universe. Imagine it as a bit cut of an enormous, unfathomable pie that we're able to study and fathom. While the total size and condition of the universe at large remain a mystery, researchers estimate the width of our conspicuous bubble to be around 93 billion light-years. A light-year measures the distance that light, the fastest thing in the universe, travels in 1 year, around 588 trillion meters or 946 trillion kilometers. So, when we examine the expansiveness of the detectable universe being 93 billion light-years, we're examining a huge stretch. Around 13.8 billion years ago, the universe burst into existence in an unfathomably strong impact. This impact began what we call the Big Bang. Since that momentous birth, the universe hasn't simply been growing. It's been advancing rapidly in its extension. Baffling forces like the mysterious dark energy give off an impression of being driving the speed increment, pushing the limits of the universe farther and farther apart. As the universe extended, matter began to mix under the impact of gravity. This gravitational force joined particles, birthing dazzling plans, stars, astronomical systems, and ultimately planets like our own dear Earth. Picture the universe passing by as these huge plans formed, progressing into the different and still maturing quarks we see scattered across the universe today. Regardless of its immense size, the universe is inconceivably empty. Assuming that we were to contract our entire nearby planet group to the size of a quarter, the closest star would still be about the length of 2 soccer fields away. This tremendousness grows just within our own Milky Way system, which is only one among billions in the observable universe, giving us a sense of the sheer size of limitless space. Now, you might inquire as to why we can't just see all that exists in the universe. There are a couple of explanations behind this limitation. Most critically, light, the fastest thing known to humankind, still takes time to travel through space. This means that when we look at distant objects, we're essentially examining the past. The farther an object is, the more its light has traveled to reach us. It's like looking through an unfathomable time machine, unrolling the history of our universe. As we observe systems millions or even billions of light years away, the real universe is growing. Imagine dots on the surface of a blowing up balloon. As the balloon inflates, the dots move farther apart. This same rule applies to the universe. Galaxies, like those dots, are floating apart as the fabric of space expands. This expansion causes the light emitted from distant objects to undergo a shift known as redshift. Essentially, the frequencies of light stretch as the objects move away, shifting toward longer frequencies, often seen as a bronze tone. Given these factors, light's travel time, the expansion of space, and the universe's continuous advancement, it's not surprising that we haven't yet fully observed the entirety of the universe. Even with our highly advanced telescopes and technology, our view remains limited by these key properties of the universe. The journey to understand the possible edge or limits of the universe has enraptured the minds of countless individuals across disciplines. While convincing answers remain elusive, 3 recognizable hypotheses have emerged, each presenting interesting perspectives on the vastness of cosmic space. The first hypothesis suggests that the universe grows unfathomably, continuing on endlessly without a noticeable edge. This idea aligns with the cosmological principle, affirming the isotropy of the universe. its consistency in appearance from any vantage point. If this principle holds, it suggests that the universe has no boundary, expanding perpetually in all directions. The second hypothesis offers an alternative view, suggesting that while the universe may indeed be limited, it lacks a clear edge. Instead, it's like an epic circle or a curved space connected to itself, similar to Earth. In this scenario, if one were to travel endlessly in any direction, they would eventually return to their starting point, like circumnavigating the Earth. The third theory, the multiverse hypothesis, presents a fascinating idea that our universe is simply one among countless others. Imagine endless parallel universes, each existing with its own set of physical laws, constants, and properties. These universes may be completely isolated from one another, operating independently, or they may be interconnected through complex systems, forming a vast and intricate multiverse. The James Webb Space Telescope, JWST, stands as a beacon of potential, illuminating the secrets that shroud the gigantic origins of the universe. This incredible instrument has an unmatched ability to disentangle the confusing past of our universe, allowing us to peer far beyond what was previously possible. The JWST is a mechanical marvel, designed specifically to observe the universe with unprecedented accuracy. Its advanced capabilities extend our vision to the earliest moments of the universe. Recently, a groundbreaking study published in the prestigious journal Nature revealed the JWST's discovery of 6 massive galaxies dating back between 500 million and 700 million years after the Big Bang. Incredibly, these ancient galaxies are far larger than expected for their early existence, challenging prevailing ideas about the universe's development and growth in its infancy. What's truly surprising about these discoveries is the level of development of these ancient systems, defying conventional models. These celestial giants display a degree of complexity comparable to our 13-billion-year-old Milky Way. The sheer number of stars inside these massive behemoths surpasses comprehension, each boasting a total mass several times greater than our Sun strikingly. One of these galaxies may even have a mass up to 100 billion times that of our Sun, eclipsing the already gigantic size of our Milky Way. The JWST's unparalleled ability to see the universe's hidden regions relies on its use of infrared light, an invisible spectrum to the naked eye. This remarkable power allows the telescope to capture the faint emissions from ancient stars and galaxies, revealing enormous remnants that have endured for billions of years. Essentially, the JWST acts as a time machine, taking us back through the ages and offering a rare look into the universe as it appeared roughly 1.5 billion years ago. The ongoing discovery of massive galaxies, affectionately nicknamed universe breakers, has overturned our understanding. It's akin to rewriting history, a shocking twist that challenges many of the models we had laid out for early galaxies. Initially, we thought galaxies formed from humble beginnings, starting as small collections of stars and dust. They were believed to gradually grow, increasing in size and complexity over time. However, the universe breakers have shattered these assumptions. When the JWST data and its high-resolution images unveiled these titanic structures, they appeared seemingly out of nowhere, upending our previous understanding of cosmic evolution. Digging deeper, scientists used spectroscopic techniques to analyze light across different frequencies. This examination holds the key to unlocking crucial insights about these mysterious galaxies. Details such as their structure, size, and distance from Earth. It's like a vast detective story, with light as the clue to uncovering the secrets of these enormous entities. The stunning revelations from the James Webb Space Telescope have propelled our understanding of the universe to extraordinary levels. This cutting-edge telescope, built by a global team of space scientists, has recently uncovered an amazing discovery: the identification of the oldest and most distant galaxies ever observed. These galaxies transport us back to when the universe was just a tiny fraction of its current age, existing only a short time after the Big Bang. The James Webb Space Telescope, out in the immense void of space, has been seeking answers about the universe. It's NASA's latest monumental instrument, capturing stunning images of stars, galaxies, and planets. Recently, it made a discovery so remarkable that it could change how we comprehend the very fabric of the universe, leaving researchers baffled and curious about its potential repercussions. When we examine the universe, we begin with the observable universe, a window into the immeasurability. Beyond this observable universe encompasses everything we can currently connect with our telescopes and space probes, including stars, galaxies, and other celestial bodies. However, it's just a small part of the entire universe. Researchers estimate the width of our observable universe to be around 93 billion light-years. A light-year measures the distance light travels in 1 year, roughly 588 trillion miles, making the scale nearly boundless. About 13.8 billion years ago, the universe began with the Big Bang, an epic explosion that triggered the immense expansion. Since then, the universe has been growing and accelerating, driven by mysterious forces like dark energy. Matter began to coalesce under gravity, forming stars, galaxies, and eventually planets like Earth. This continuous development shapes the universe's colossal size, allowing us to observe only a small part of its vastness. Despite its massive size, the universe is surprisingly empty. For example, if our entire solar system were the size of a quarter, the nearest star would still be about 2 soccer fields away. This immensity stretches just within our own Milky Way galaxy, which is just one of billions in the observable universe. We can't see everything due to 2 primary factors: the time it takes for light to cross space and the universe's ongoing expansion. As galaxies move away from us, their light shifts to longer frequencies, making some objects too distant to detect. Scientists use units like light-years to measure these vast distances. Our Milky Way is about 100,000 light-years wide, and the closest star to the Sun, Proxima Centauri, is 4.24 light-years away. Observing galaxies billions of light-years away lets us explore the past, seeing them as they were billions of years ago. This vast expansion also means our observational limits are constantly being pushed as the universe accelerates. 3 primary theories try to explain the scale of the universe. It could endlessly grow, it could be limited but without a clear edge, like a giant circle, or our universe could be one of many in a multiverse, each with its own physical laws. These theories, while speculative, spark scientific curiosity and philosophical reflection, testing how we understand space's limits and existence. The James Webb Space Telescope has provided crucial insights into early universe development. Designed to observe the universe with unparalleled precision, it has recently discovered 6 massive galaxies dating back between 500 and 700 million years after the Big Bang. These massive galaxies surprisingly appear much older than expected, challenging current theories about cosmic development. The JWST's ability to see the universe's mysterious regions depends on its infrared capabilities, allowing it to observe ancient stars and galaxies that have existed for billions of years. The discovery of these universe breakers suggests that early galaxies were far larger and more developed than previously thought, leading to a deeper understanding of the universe's history. The James Webb Space Telescope, JWST, continues to revolutionize our understanding of the cosmos, providing answers to long-standing questions and raising new, deeper inquiries about the universe's formation and evolution. Its state-of-the-art capabilities are unraveling mysteries that were once beyond our reach, including the precise nature of the earliest galaxies and the processes that shaped them. JWST's discoveries push the boundaries of our knowledge in unprecedented ways, highlighting the need for even more advanced tools to further explore the unknown. One of the most significant aspects of JWST's contributions lies in its ability to observe the universe in the infrared spectrum. Unlike optical telescopes, which detect visible light, the infrared capabilities of JWST enable it to peer through cosmic dust and gas clouds, unveiling celestial objects that are otherwise hidden from view. This allows scientists to study the formation of galaxies, stars, and planetary systems in their infancy, offering insights into the building blocks of our universe. As a result, the telescope has already provided images and data that challenge conventional models of cosmology, especially concerning the timeline and complexity of early galaxies. One of the most surprising discoveries made by the JWST is the identification of supermassive black holes in the early universe. These colossal objects, which weigh millions or even billions of times more than our Sun, were thought to form only later in the universe's history. The fact that they were present so soon after the Big Bang raises profound questions about how such massive objects could have formed so quickly. Scientists are now grappling with the implications of these findings, as they suggest that the processes that led to the formation of black holes may be more complex than previously believed. Moreover, the JWST's observations have provided unprecedented views of the cosmic dawn, the period when the first stars began to shine, ending the so-called cosmic dark ages. This pivotal moment in the history of the universe marks the transition from a featureless expanse of hydrogen gas to a universe teeming with stars, galaxies, and other structures. By studying this era, astronomers hope to understand how the first light illuminated the universe and how galaxies began to evolve from the primordial gas clouds. The JWST's ability to capture detailed images of the farthest reaches of the universe also has significant implications for our understanding of dark matter and dark energy, two mysterious substances that make up the majority of the cosmos but remain largely invisible and poorly understood. The more we observe distant galaxies and clusters, the more we can infer about the distribution and behavior of dark matter, which exerts a gravitational influence on the visible matter we can see. Similarly, by tracking the expansion of the universe, JWST's data will help refine our understanding of dark energy, the enigmatic force believed to be driving the accelerated expansion of the universe. These discoveries are just the beginning. As the JWST continues to explore the vastness of space, it will undoubtedly unlock more secrets about the fundamental nature of our universe. Each new discovery builds upon the last, offering a deeper and more comprehensive view of the cosmos. While questions remain, the JWST is fast becoming the most powerful tool in our quest to understand the universe and our place within it. As we look to the future, we can only imagine the groundbreaking revelations that await us in the coming years.